Good afternoon, everybody. Today I am going to tell you about the thermodynamic derivation of the phase rule. As we all know, the phase rule is given by F is equal to C minus P plus 2, where F is the degree of freedom, C is the number of components, and P is the number of phases. So this means when we are studying multi-component system where there are many phases, then how will we arrive to the Gibbs phase rule, which is given by the F is equal to C minus P plus 2. Now, as we all know that the degree of freedom is given by the definition that it is the number of the variables which must be fixed in a system to define that system completely. That is the degree of freedom. So actually that can be obtained when we have the number of the variables less the number of variables which are due to the system being in equilibrium. So we can say that to calculate the thermodynamic, to calculate the degree of freedom, we should have the number of variables, means the total number of variables which are present in that system minus the number of variables which are defined by the system due to its being in equilibrium. Means if this is A, the number of variables, and B is the number of variables which are defined by the system, then F will be the means the degree of freedom will be A minus B, means total number of variables minus the variables which are defined by the system due to its being in equilibrium. So let's come over to this how we will calculate the total number of the variables. Now let us consider a heterogeneous system which is having a number of phases. So suppose this is our system and it is having a number of phases given by P1, P2 and P3, and suppose there are a number of components in it, C1, C2, C3. So if we know the composition, suppose we are having a single phase and we know the composition of one of its component. Suppose there are two components only, and we know the composition of one of the component, then the composition of other component can be easily calculated. That will be 100 minus that. Let me explain it with a very simple example. Suppose we are having a box of marbles. Suppose we are having a box of marbles. Okay, and there are red marbles and there are green marbles and there are total 100 marbles. The total marbles are 100, and suppose there are red marbles are 40. Then we can easily calculate the number of green marbles. The number of green marbles will be 100 minus 40. This means if we know the concentration of one of the component, the concentration of other component can be easily calculated by difference. Okay. Now suppose there are red marbles, there are 10 green marbles and there are blue marbles also, and we have to calculate that how many blue marbles will be there in this system. So we can calculate that also very easily. This red marbles plus green marbles minus 100 minus the sum of red and green marbles will be the blue marbles, means that will be 50. The blue marbles will be 50. How we calculated it? We know the concentration of two of them and the amount of the third can be easily calculated. This means that for when one phase is present and suppose there are three components, we need to know the concentration of at least two components so that we can have the composition of this whole phase. Okay. This means that when one phase is present, we should know at least how many C minus 1 concentration terms for one phase. Suppose this is one phase, this is P2, this is P3 and this is P4. Here I am considering single phase just for your ease of understanding. And we all have seen this, that C1 and C1, these are in equilibrium. Components are in equilibrium. So another component is there, C2, this is also in equilibrium. Similarly, suppose there ith component, and so this is also in equilibrium with all the phases. But let me first explain it to you for your understanding. That suppose consider to make it easy, to make it comprehensive for you. Consider a single phase. In single phase, suppose there are two components, then if we know the concentration of one, we can calculate the concentration of the other. If there are three components, if we know the concentration of two, we can calculate that of the third one. So how many concentrations should be known to us? Actually, that should be C minus 1 for one phase. So for one phase, we should know how many concentration terms? C minus 1 concentration terms. You should have understood it by this example. We should know C minus 1 concentration terms in order to have all the about the composition of the whole phase. So suppose there are P phases. Suppose in a system we are having P phases, then how many concentration terms should we know? It should be P into C minus 1. A simple maths involved here, P into C minus 1. And now, as we all know that along with the composition, the other two variables which must be known to us are the pressure variable and the temperature variable. Pressure, temperature and composition, these are the three variables which must be known to us. So, one is the composition. I have told you that for P phases, we will need how much? P into C minus 1 concentration terms should be known to us. So this is about the concentration. Now the other variables are pressure, temperature, and they are same for all the phases. So we can consider that these are two variables. So the total number of variables which will be in a system, that will be P into C minus 1 plus 2. For 2, it is one is the temperature and the other one is the pressure variable. So the total number of variables are given by P into C minus 1 plus 2. Now we come over to the another factor, which is the number of variables which are defined by the system itself due to its being in equilibrium with the system. This I will tell you just now. As we have seen earlier, that while explaining the chemical equilibrium, we have seen that the chemical potential of a component is same in all the phases. Suppose there are three phases, then the chemical potential will be same. Let us consider chemical potential of one component number 1. Let it be mu1. Mu is the symbol for chemical potential. Let for one component, for component 1, let its chemical potential be mu1. Then this chemical potential of component number 1 in phase A, will be equal to the chemical potential of component number 1 in phase B. Let it be, I have shown this is PA is actually phase number A and this is phase number B. For easy understanding, I have written like this. So the chemical potential of component number 1 will be equal in phase A will be equal to the chemical potential of component number 1 in phase B. Now suppose there are three phases present, what will happen? Again the chemical potential of component number 1 in phase B will be equal to the chemical potential of component number 1 in phase C. So these are three phases A, B and C. Suppose there are three phases A, B and C. And the chemical potential of component number 1 is mu1. So mu1 in phase A will be equal to mu1 in phase B and mu1 in phase B will be equal to mu1 in phase C. So in all, here we require equation number 1 and equation number 2. We require two equations to explain the system, to explain the chemical potential equality. We require two equations. Now suppose there are 4 phases instead of 3 phases, there are 4 phases. So what will happen? The other equation will be mu1 in phase number C will be equal to mu1 means chemical potential of component number 1 in phase D. So this is one more equation added when we have increased the number of phases. Means when there were three phases, then the number of equations which were used to define that system was two equations. And now when we are having four phases A, B, C, D, then the number of equations which are being used are how much? Three equations. Similarly, we can see that when there are five phases, then the number of equations will become 4. This means for P phases, suppose there are A, B, C, D, so suppose there are P phases, number of phases, then the number of equations that will be utilized will be how much? P minus 1 phase. P minus 1 equations. So we will need P minus 1 equations to define the chemical potential for the P phases. So this comes out to be P minus 1 equations. So this is only for component number 1. Suppose there are C components in the system. So we have for one component, we have how many equations? P minus 1 equations. So when there are C components, it's a multi-component system. So suppose there are C components. So when there are C components, then we will have C into P minus 1 equations. So these are the number of variables. Which are defined by the system because of its being in equilibrium. This is B. And the earlier I have calculated the total number of variables, that is P into C minus 1 plus 2. This is A. So now we have to calculate the degree of freedom. The degree of freedom will be the total number of variables minus the variables of the system which are defined by its being in equilibrium. So F will come out to be, here you can see this is degree of freedom, A minus B. A is that term, I will put it in box. This is A term and this is our B term. So F will be given by, F degree of freedom will be equal to A minus B is P into C minus 1 plus 2. You can see they were there, and minus how much? C into P minus 1. We can calculate it now. PC minus P plus 2 minus Cp plus C. Now let's calculate it. PC will get cancelled by this. PC, one is positive and the other one is negative, and what we get is C minus P plus 2. And this is our Gibbs phase. So this is the thermodynamic derivation of the Gibbs phase rule. Let me summarize it once again. For the thermodynamic derivation of the phase rule, we need to have the number of variables and the number of variables which are defined by the system itself. We will calculate both of them, and the degree of freedom is given by their difference. So first of all, let us calculate the number of variables, the total number of variables in the system. Now suppose there is a system suppose there are two phases, and we are having a component in it. There are two components in one phase. Then we can get the concentration of the other component by subtracting it by 100. So this means that how many concentration terms we need to have C minus 1 concentration terms in order to get the composition of the whole system. I have just now explained you with the example of marbles, red, green, and blue. So in this way, for one phase we have C minus 1. We should know C minus 1 concentration terms. Now if there are P number of phases, we need to know P multiplied by C minus 1 concentration terms for P number of phases. Now, as we all know that the temperature and the pressure, these are the two variables and they remain the same in all the phases. During equilibrium, they will remain the phase. So, these are two variables. We will sum them up. So, what comes out to be the total number of variables will be P into C minus 1 plus 2. These are our total number of variables. Now, let's come to the variables which are defined by the system itself due to its being in equilibrium. So, for that, we need the help of chemical potential. Now suppose there are three phases. I have taken here three phases because for two phases we take free energy into consideration, not the chemical potential. So when there are three phases in equilibrium, then we need the equations we need to define the system will be for one component. For three phases we need two equations. Similarly, if there are three phases we will need two equations, and when there are four phases we will need three equations. Similarly, when there are five phases, we will be needing four equations. This means that three phases we need two equations, for four we need three. This means if there are p phases, we will be requiring p minus 1 equations. Now, this is for one component only. Suppose there are c components, then the number of equations required for all the components will be c into p minus 1 equations. Now, let us calculate the degree of freedom. The degree of freedom will be given by this minus this, and this is that thing minus this one, and this comes out to be, when we do the mathematical part, that comes out to be c minus p plus 2, and this is our Gibbs phase. Thank you so much.